multiple different programs for that. If you were to write your program this way, then I would be very happy with that program, because then I can, without, the master controller for the pool of machines, doesn't have to come back to you. Just can say, well, it has this MapReduce structure, so if I have 10,000 machines, I will do these many machines for the map part, these many machines for the reduce part, and I'm done. Okay, the architecture that supports, so you can write your form, your program in MapReduce form, and then there are architectures that support, seamlessly for you, this scheduling at runtime as to which machines get used. Okay, and those details are what I will talk about next. A little more into how that actually happens. Okay, but this should give you, first of all, what is it that the MapReduce architecture is trying to do? What sort of problems can it support? What sort of problems it can't support? Okay, and thankfully, many of the problems you would be interested in the search engines actually are of this form. Okay, and that means you can write MapReduce type of programs for it. So, in fact, there are open standards now. Originally, MapReduce came up in Google file systems, but there is Hadoop right now, which you can use. It's open, Apache gives it to you. And then you can try these out. There should be some course which makes you do Hadoop programming. Yes?
So you said that...
Maybe I can make program part 2 be based on Hadoop. Yes.
So you said that it is because that a lot of search engine programs can be supported by this architecture, but it seems from what you just said that the architecture was created because of search engines. That's why.
It's both ways. Yeah, it's true. I mean, in fact, because you generated MapReduce kind of parallelism, because you basically wind up doing simple operations, repeat simple operations multiple times on multiple pieces of the data. That was coming up in the search engines, and so they came up with the MapReduce architecture in Google. In fact, the two guys who, the usual public understanding of what makes Google tick, at least whenever people try to write you a little article, would be PageRank. Okay, it's not even clear whether Google actually uses PageRank. Other than that, if you ask what's my PageRank, it'll give you some number. Okay, but it's not at all clear that Google uses PageRank, and even if they do, it's not patented. Anybody can use it. There are all sorts of ways of using this stuff. The real impediment, the barrier to entry, is the server farms, and the fact that they were one of the first to support this MapReduce architecture. It's a systems development, which makes me depressed because I don't particularly care about system stuff. But it's very important to support. So if you go into any of these companies, the first few days you will be told how to use this architecture. How do you write your little program? And if you write it in this high-level language, then the entire server farms that are available for Google can work on Google or Facebook or whatever, can work on your computation. Okay, so somebody had to actually develop that architecture, and those two guys really are the first two Google fellows. One guy is Sanjay Dhimawar, and the other guy is Chapti. And those two guys developed the Google file system and MapReduce architecture. Okay. Again, it's not that this is like equal-to-empty kind of a difficulty. It's a different kind of difficulty. Making sure that architecture works, making sure that it's fault tolerant, making sure that it works even as more and more machines are being thrown in. It's like developing an operating system. It's in fact developing an operating system for the cloud. That's what this is. Okay. So anyway, I will get to this part. Can we get MapReduce parallelism to indexing? I'll get to that after I'm done discussing a little more details about MapReduce architecture. For that, I'm going to use the chapter you read. Okay, this is Ulman and Rajaram chapter on MapReduce. So all they're saying is their slides. You have conventional memory with a CPU and a memory, and then there's a disk. And then I'm not going to go into this slowly, but basically you have many machines available cheaply, and you want to be able to use them to improve the speed of your computation. Okay, this is the architecture that you can think of. Essentially, you have multiple racks of computers, okay, which are connected by one switch, and then they're all again being looked. Each of the racks is being looked at by a master controller. All the racks together are being looked at by a master controller. Okay. Okay, so that's your mental view. So if one of these machines goes down, it doesn't bring down the entire system. Okay, because there is replication. So whatever this guy is doing, this guy can do too. You can actually just change it last minute. And in fact, so even if this switch fails, then essentially I would stop using this entire rack. I will use some other rack. Okay. And if the master controller fails, I will stop using that master controller, use another master controller. It's all about replication. Okay, and we will look at that in detail a little bit later. The first thing to be able to do computation on this is where is the file? Right. I mean, I have lots and lots of machines. The one part that my biology example doesn't have is each of them gets to have one, little glass plate. Okay, but suppose I actually have, all the glass plate data is in this huge stack somewhere at the end of the room, and these undergrads are being asked to go take these. I mean, I have nothing against undergrads and high school students. I summarize see that. So please do consider doing research with me, even if you're one of those. But as they are bringing out one of these glass plates, suppose the glass plate fails, that it breaks down, then you have lost data. So before you even allow them into the room, presumably you would have to say, for each glass plate, you make 3 copies, first of all. So if you, break one, then you can say, okay, steady, my friend, now carefully take one out. Okay? And then, so until they came, it was the glass plate rule. It was one file, really, with replication thrown in. And when they go, they bring each of their glass plates, that's their part of the file. And they only have to work on their part of the file. You see what I'm saying? So that's what you need for files too. So what I did for glass plates, you need to do for files. And so that's stable storage. I made stable storage for my glass plate by making multiple copies of the plates, so that if they remove one and that falls down, then not everything falls down. And furthermore, to make sure that if he picks all 3 at the same time and drops them, all 3 are gone, I put one here, one there. So that you really have to be adversarial and hate my lab for you to run around and kill all of them. Okay? It's the same idea we'll do for the stable storage too. First order problem is nodes can fail. How do we store data persistently? Okay. So distributed file system. That's a Google file system that was developed. Okay. So you come up with a global file namespace. There are examples, GFS, Hadoop, and Cosmix is there because Anand Rajaraman was giving a talk. I guess he was one of the people who was doing this course, and his company is Cosmix, which got bought up by Walmart last year. Okay. And then you have huge files. You have huge stacks of glass plates, essentially, huge files. So hundreds of gigabytes to terabyte size. And the good thing is the files are rarely being updated in place. Okay, the files don't change too often. If at all they change, you just append it to the end. Okay, so to that extent, so data is rarely updated in place. So the GFS actually exploits, the MapReduce exploits the fact that, as he said, the kind of computation you want to do has this coarse-grained notion of parallelism. GFS exploits the fact that you have large files, but people aren't writing in all parts of the files at the same time. Okay, and so more like reading is what you're doing. You're not writing. On the web, most of what you're doing is reading. Okay, and then of course, if the data does change, you tend to throw it as the append. At the end of the day. Now, if that is the case, then what can I do? I essentially make chunks of the file, just as I have my class plate storage has been put into individual class plates. Okay, so here I can make chunks of the file. The large file has been split into multiple chunks, and each chunk can be some reasonable size that even a cheap computer can hold in main memory. Okay, so here is, let's say, 62 to 64 megabytes. Now each chunk is then replicated. Each class plate, I said I put one there, one there, one there, so that's like replicating the chunk on multiple CPUs. Okay, the more you replicate, the more stable you are. Okay, and then you need to put replicas in different racks. Put one there, one there, one there, so that not all racks go at the same time, because there is one, master plug that somebody pulled out, and the entire server farm went bleak. Okay, so you avoid that. And then there is a master node which basically stores metadata about which chunk is where. File is the following sequence of chunks, and this chunk is there, this chunk is there, and so on. So it has a pointer system. Master node itself would be replicated. So that if this master node goes down, some other master node will take its place. Everything is replicated within means, within reasonable bounds. Okay, and then you provide a client library for file access, so that people don't need to know that that's what is happening when they are trying to read a part of the file. So the actual way, just as your normal CPU doesn't ask you, so tell me which sector of your disk are you interested in reading right now, and in which case you will start doing computing, right? It just figures out which sector is the one that you're looking for, and looks, go seeks that sector. Similarly here, the master controller will tell which chunk you're supposed to be looking for, and then where it is located, and so you can go get it. So that can all be supported as a client library. This is what your Hadoop, for example, supports. If you download Hadoop, this is the kind of support you have. From the file system point of view, it's just you have big files now. Basically, large size files which don't fit in any place, and you want replication. Okay. So then, if I have this, right, and I guess, I'm not really sure, I can probably start talking about the word count and we'll come back next class. So if I have this, then, if I have a big file of the document corpus, then essentially I would be putting, 64 megabytes each into one chunk. And then I will replicate them, and I'll know where multiple places where each of these chunks are. Okay. So now I want you to think in the next 2 minutes, I guess, just the idea of counting words from a file, counting the words and the number of unique words, and for each word, what's the frequency of the word. And I hope that you use a real operating system one time in your life, such as Unix, and so we'll use some Unix commands. Okay. So we have a large file of words, and one word at a time. Count the number of times each distinct word appears. This can be used in multiple places. You can, for example, count, web server logs, for example. So entire file fits in the memory. Entire file is too large for memory, but all word count pairs will fit in the memory. These are the separate cases. The case 3 is file is on disk, too many distinct words to fit in the memory. Now this is the first time it becomes interesting for us. The other two are too cheap. Okay. Now what do? I can do a sort on the data file, and I pipe it to unique with a -c. That basically just gets me out word and count. That's what the Unix does. So this is, if I have one file in the disk and I want to find out the word occurrences, this is what you need to do in Unix, right? Now if I have multiple files, there are multiple files, and I want to compute the word count across all the files. Okay, then what I would need to do is essentially I would have to do the words from all the documents, sort them, and then do Unix. Okay, so for this one is basically easily parallelizable. For each document, I can have one machine doing the words from the document. Okay, so you already have this written in a sort of a MapReduce form. Okay. So words takes a file and outputs the words in it, one in a line, and this sort of captures already, some kind of a parallelism, this MapReduce kind of parallelism. This is obviously naturally parallelizable, which is not surprising to you because of all the discussion we already done. what I'll do next class is come back and say that there are different examples of MapReduce you have seen till now, and there is one simple idea called key-value pairs. You have a key and a value, and all that MapReduce does is you can think of at an abstract level as input is a whole bunch of key and value pairs. And in the map phase, essentially these key values are converted into different key value pairs. Okay? Right? And then in the reduce phase, these intermediate key value pairs are grouped, saying for each of these intermediate, the blue key, these are all the values, the yellow key, these are all the values, and so on. So for example, this key could be the word name. These are the number of times the word has occurred, so 1, 1, 1. Now after that, I can reduce it by adding these 3, and I'll get the word count, for example. Okay, so this key value metaphor is what you want to think of. It's the abstract data type for MapReduce parallelism is the key value metaphor. So whatever you're trying to do, whatever computation you're trying to do, think of trying to visualize the input as a bunch of keys and their values. And then the map will convert it into intermediate keys and their values. And then you group the keys such that all the values on a particular key come together, and then you reduce. The reduction can be any arbitrary operation. It can be, addition, it can be, whatever you want. For word count, you just have to add. Okay, we'll start here next class and then look at, for example, how to do this for indexing and how to do this for page rank computation. We'll also go a little more details.